Hello, welcome to my YouTube channel, and today we are going to be looking at the acoustic and clinical models for neonatal respiratory distress prediction. My name is Abisha Baingana, and last week we looked at the exploratory data analysis for the different data sets that we are working with, and today we've moved on to the 4 main models that have been built. So this is a roadmap of what we are going to be looking at, in today's presentation. For the dataset overview, we are working with 2 models, so with 2 datasets. That is the acoustic dataset that has about 6,000 samples with 6 classes and 33 features extracted, as well as the clinical dataset with 30,000 records and 3 burden scenarios, that is low, moderate, and high burden, with about 15 plus features extracted. So our model overview, we are going to be looking at 4 models today. That is the ResNet-18, the XGBoost classifier, as well as the logical regression model. So model 1, ResNet-18, this is the architecture of ResNet-18, and basically we are starting from the feature extraction, moving on to reshaping and placing those extracted features in different batches, and then moving on to the initial conversion. Then you have 4 main layers of this architecture. That is the ResNet block 1, and each layer has the ResNet block 1 and block 2. So after going through the 4 layers, we start with 64 dimensional features all the way to 512 dimensional features. Then we shall move on to pooling, where we get the adaptive average pool, and then the output, which will be a fully connected 512 dimensional feature, and our output will be class probabilities. Then these were some of the results from the training of the first model. And here we have our training loss curve, where the training loss is seen to steadily decrease, whereas with validation accuracy, the accuracy was seen to improve with more epochs. And moving on to model 2, which is the XGBoost model, but for the acoustic dataset. And still we are starting with the 33 extracted audio features. Then we move them through an ensemble classifier with about 200 trees, with each tree having a maximum depth of 8 all the way to the 200th tree. And after all these trees have after these trees, we move on to the voting, where we do weighted voting, and then we look at the learning rate as well as the subsample. And our output is going to be 6 class probabilities. And these were some of the results for our training from model 2. We have the XGBoost training progress, where we look at the training loss and the validation loss. And then we have an overfitting indicator due to the running of many epochs compared to the number of records that we had in that data set. So moving on to model 3, which was also an XGBoost, but this was based on the clinical data set. We still started with the 15 extracted features, such as the heart rate, the gestational age, as well as the birth weight and others, and we pass them through an ensemble. But here, for the clinical data, we are looking at 100 trees. And so here we move through, when we move through the trees, so in the ensemble, once we are done with the trees maximum depth 6, we move on to weighted voting still, and then we also look at the learning rate, and from there our output will be a binary risk score, unlike the other side where our output was 6 class probabilities. And for here, we noticed that the spatial oxygen percentage and high respiratory rate are actually the strongest indicators of neonatal respiratory distress. And these were some of the results we got from the training of model 3. We look at the confusion matrix as well as the overfitting indicator, and we also have the area under curve for the clinical XGBoost. And then moving on to our 4th model, which is the final model. This is a linear regression model based off the clinical data set. And still we start by extracting the features, and then we move on to linear combination, where we look at different coefficients. And from there, we combine both the combine the coefficients as well as the extracted features, which act as the input. And from then we move on to the next step, which is activation, where we use sigmoid activation, and our final output is still a binary risk score, which is interpreted, and we shall have a high score as well as a low score. The high score should be higher than 0.5, and the low score can be less than or equal to 0.5. And from here, I want to note that the linear regression was actually the smallest because it only took about 12 coefficients, and it's clinically trusted because the doctors would understand why the risk is high or why it's low. And it was the fastest because its training time was about 40 something seconds. So these were some of the coefficients. We have the positive coefficients, which increase risk. With these coefficients, such as the respiratory rate as well as the heart rate, if they are higher, then that means that there is an increased risk of that neonate having respiratory distress. Then we have the negative coefficients, such as the gestational age, whereby with the higher the age, then of course the lower the chances of having respiratory distress, as well as the birth weight, the APGAR, and the spatial oxygen. So these were some of the results from the model 4 training. Same as the model here, we'll look at the confusion matrix and the area under curve. Then this was just a summary or an overview of the models that we've looked at, and we are comparing them based on the accuracy, the area under curve, as well as the training time. And from here, from this table here, we can see that the logistic regression was actually it was the fastest in terms of training time because it only had 49.2 seconds, whereas with accuracy, the XGBoost for clinical data was actually the one that had the highest accuracy, followed closely by the logistic regression. So we also noticed some limitations in the models that we had, and we categorized them into 3 main types of limitations. We have the data limitations, technical limitations, and the clinical limitations. And the data limitations, we have the data sets we are using do not actually have neonatal audio, because we are looking at audio recordings from toddlers, infants, and adults. And then the clinical data is actually a synthetic data set, which is also a limitation in that we're not looking at actual real-world data. And then there is a class imbalance in the acoustic data set, whereby we had only about 22 samples out of the 6,000 plus samples for Strider, yet it is one of the most important acoustic clinical factors. And then we have the pediatric adult data proxy, whereby the data was leaning more towards the adults than the neonates. And then for technical limitations, we had the unpaired modalities, because the audio data that we have is not actually connected in any way to the clinical data that we had. Then there is no joint distribution learning. So the only fusion that we can have is late fusion, and we cannot have any early fusion. And feature engineering in this case is actually all supposed to be done manually. Then for clinical limitations, the data is not validated in real patients. There is a domain shift from pediatric data, and it requires prospective clinical trials in the future. Then moving on to our evaluation metrics. So we are looking at what did we base on to calculate the accuracy, the precision, the recall, as well as the F1 score. So with accuracy, we looked at the true positives and the true negatives and divided by the total to get the overall correctness. For precision, look at true positive over the sum of the true positive and false positives to get predicted positives, which are correct. Same thing for recall, we look at true positive over sum of true positive and false negative to get those actual positives which were caught. So when we look at the risk prediction, this was classification metrics, and when we look at risk prediction, we have the area under the ROC curve, and this one helps us to distinguish if the risk is high or if it's low. And then we have the ECE, or what we would call the expected calibration error, and from here we get to see that do the probabilities that we get from our models actually match, or do they align with what is in reality? So our key takeaways from the models that we trained were, for acoustic models, we had the ResNet and the XGBoost, and we know that For ResNet, this one would it learns complex hierarchical audio patterns automatically, whereas the XGBoost is faster, it's interpretable, and it's nearly as accurate. And the MFCC features, or what we would call the male frequency cepstral coefficient features, are the most discriminative audio signals. Then for the clinical models, we have the simple logistic regression, which performs almost as well as the XGBoost, and feature importance here matches the well-established clinical literature. And when we move on to see, based on what our needs are, which model would you select? So if you're looking for interpretability, logistic regression would be the best model. If you're looking for best accuracy, the XGBoost. For deep learning, ResNet-18. And we decided to go with the ResNet-18 instead of ResNet-50 because based on the number of samples that we had, which were about 6,000, if we were to use ResNet-50, would have an issue of overfitting, because ResNet-50 works best with datasets that have about 10,000 samples onwards, unlike ResNet-18, which works best with datasets that have less than 10,000 samples, which was working well enough for our dataset. So our next steps, we are going to be looking at what we've so far completed, what is in the pipeline, and what is in the future, what is in store for us. So so far what we've completed is the training of the 4 models, which have been trained and validated. And then we have what we're looking towards is the fusion of the models, both models from the clinical data and the audio data. So we are going to be doing lead fusion, and we are going to use a naive-based ensemble fusion. And then we are looking at edge optimization, where I want to do quantization for low latency development. And then we are also seeing clinical validation in our future. So our immediate priority right now is to work on the lead fusion ensemble. Then these were some of the references for our data sets, and as well as thank you very much. This has been Abisha Baingana, and I would love to acknowledge our data providers, our institute, as well as our supervisor. Thank you.